So last time we started defining what's the topology and so on. So X any set, right? A topology on X means this thing is a subset of the collection of all subsets of X, right? 2 to the power X means the collection of all subsets of X satisfying the following. The subsets empty set and X should belong to this. If U1, UN are in tau, then their intersection will be in tau. In other words, tau should be closed under finite intersections. And third, if we have any collection of elements in tau, then their union is also in tau. In other words, tau will be closed under arbitrary unions, closed under finite intersections, but closed under arbitrary unions. Okay, if this is the case, then we say that tau is a topology on X. Okay, now this thing is the smallest topology, weakest topology, or smallest topology on X, and you may take the whole power set, the collection of all subs, that's the strongest topology on X. Okay. The topologies on R or Rn are the ones we are familiar with. So, for example, we have on X, we have so-called the standard topology. What is this? We call it tau standard. It is the following one. So I have to tell you what are the elements of this collection, right? What are the open sets? Open sets are subsets of R such that if X belongs to U, then there is some R positive, so that X minus R, X plus R belongs to U. So subsets of R which satisfies this property are called open sets, and this collection forms a topology which we call the standard topology on R. Okay. Similarly, standard topology on Rn, which we denote usually like this, standard topology is defined as follows. So the same definition, standard topology on R, standard topology. So they are subsets of Rn such that if X is in U, then there is some R positive such that the ball with center X and radius R lies in U. So what we mean by this ball is just set of all Y's such that X minus Y less than R. So okay, so here, so this is dxr, r being the radius of this ball. Okay. These are the topologies we are familiar with, right, from calculus courses. What else? Okay, let me switch to the board. Okay. Here is another topology. Real line with double origin. What is this? It is the following. X is the following set. It's a quotient set. So it is just this product. You take two copies of real line, okay, R cross -1 and R cross 1, and then you identify the points x comma -1 with x comma 1 for any x in R, provided that x is not 0. So what you do is the following. You take two copies of real line, okay? Suppose this is just R cross 1 and this is R cross -1, and here is 0, 0. Actually, this is, maybe we should write 0 comma 1. This is 0 comma -1. And then what you do, for any point other than the origin, you look at these points, x comma 1 and x comma -1, and you regard them the same. In other words, you just glue these two copies of real line at every point, okay, at every point, except the origin. What you get is something like this. This is not a realistic picture because this space cannot be a part of or a subset of Rn. We will see that this is a non-Hausdorff space and Rn is Hausdorff. I'll tell you what they are, what they mean, and therefore this space cannot be regarded as a subspace of Rn. Therefore, this picture is not realistic, right? I am drawing this in R2. So, but the picture is something like this. So you have real line, and you have two origins. Okay, two origins. That's why this is called real line with double origin. What are the open sets? What are the open sets? Open sets are, for example, this is an open set. This is an open set. What about open sets containing this point? an open set containing this point is actually nothing but the image of an open set containing this point. So an open set containing this point is something like this, right? It contains a ball like this. You look at the image of this guy in the quotient. What is the image then? So it is this point plus two intervals like this, okay? So a neighborhood of this point is this gadget. What about a neighborhood of this point? A neighborhood of that point is so a neighborhood of this point is this point, or maybe I should draw it here first. A neighborhood of this point is something like this, and a neighborhood of that is this. So it is this point plus two intervals like this, okay? Yes. What do you mean by close enough? Yeah, of course, you may take an open set like this. You mean this, right? So take a point here, but you may take an interval like this. Yeah, sure, you can do that. Oh, of course, as a neighborhood of this point, you can, for example, a neighborhood of this point is the whole space. You can take the whole space as a neighborhood because it belongs to the topology, okay? Or you may, for example, as a neighborhood of this, you can take this interval and this point also. That's also possible. It's also an open set containing this point. But this point has a neighborhood which excludes also this point. Okay, that's the point I want to make actually. But the observation is the following. These 2 points do not have disjoint neighborhoods. Any neighborhood of this contains intervals like this, and any neighborhood of this contains intervals like this. Therefore, although these points are disjoint, their neighborhoods cannot be disjoint. That property tells us that this space is not Hausdorff. Actually, I'll clearly, I will carefully define all these concepts. Now, I am just telling you, it's Hausdorff or not Hausdorff, but I'll make them, you know, yeah, okay. Now, let me now make all these definitions more explicit. Sıcak mı oldu? Bana mı öyle geliyor? Okay. A topological space X tau is called T0 if for any xy in X with X different than Y, there is an open subset U in tau so that either X is in U and Y is not in U, or X is not in U and Y is in U. So if you have such a space, we call it T0. So what it means is the following. If you have two distinct points in this space, there is one open set containing one of them, which do not contain the other one. But you cannot have control that open set to contain which points. It may contain this one and not contain this one, or vice versa, but you don't have control of that, okay? If this is the case, we call that space T0. Okay. Similarly, X is called, okay, X is called, I say X, but actually I mean, X tau. Okay, so but once the topology is understood, what the topology is, you don't have to say each time X tau, you just say X. Okay, similarly, X is called T1 if for any xy in X, there is some u in tau, so that X is in this u and Y is not in U. So this time you have the control. You say that if I am given 2 points, then I can find an open set containing this one, but not this one, okay? And of course, similarly, there is an open set containing this one, not containing the other one. So if this is the case, we say that the space is T1, okay? Of course, right, if a space is T1, then it is clearly T0, right? This is a stronger property. You have an open set satisfying this, but actually you can choose that open set so that it contains X and not Y, and vice versa. Okay. Silgi biraz sesli bir silgiymiş. Okay. Now finally, X is called T2, or we just say Hausdorff. If for any xy in X with X and Y are different, there are open sets open subsets UV of tau so that X is in U, Y is in V, and U and V has no common point. So we have open sets like this, okay? Of course, this property is stronger than T1. In T1, you have both U and V, but U and V may intersect. There is no assumption saying that they have to be distinct, disjoint sets. But here we require that these open sets are disjoint. So clearly we have these implications. Any T2 space is T1 and any T1 space is T0. Okay, now, so as a remark, the real line with double origin is T1, but not T2. It's not Hausdorff because as I said earlier, these 2 points are different, but these 2 points do not have disjoint open sets containing these points, because any open set containing this contains open intervals like this, and any open set containing this point also contains intervals like this. Therefore, those open sets will intersect necessarily. However, this is T1. Why is that? Because if you have 2 points, you can always find an open set containing one of them and leaving the other point outside. Okay, so it is T1 space. T1 olup da T0 olmayan, pardon tersine T0 olup da T1 olmayan uzay, o neydi? O da basit bir şeydi ama şimdi hatırlamıyorum. Finite topoloji bulamıyorsun galiba da. Neyse şimdi hatırlamıyorum. Bu quotient topolojiden daha detaylı da bahsedeceğim. Şimdi hani kabaca söyledim ne olduğunu ama onu söyleyeceğim yani daha detaylı olarak. Yani şu arada şeyi de söyleyeyim. Example 3 mi olacak bu da? Any metric space is a Hausdorff right? A metric space is of course a topological space. We know what the open sets and so on. And why it is Hausdorff? Because it is Hausdorff because of the following. If you have 2 points, you measure the distance between them. Let's say R is the distance between X and Y, which is a positive real number if X and Y are different. Then just take the ball with radius r/3 about x and y. So you look at this distance, divide it into 3, and then just look at this ball and this ball. Clearly, these balls are open sets containing x and y, and they are disjoint. Therefore, any metric space is Hausdorff. Okay. Equivalence of topologies. So when do we say two topology on a set, X are equivalent? Okay. Now a function f, let's say from a topological space to another topological space is called continuous if f inverse of u inverse image. What we mean by inverse image, of course, the set of all x's such that f of x is in u. So is open in x whenever x is open in x. So if we have a map from a topological space x to another topological space y, we say that this function is continuous if what happens? If the following holds, whenever you have an open set in y, its inverse image has to be an open set in x. If this is the case, then we say that this map is continuous. Okay? In mathematics, inverse image is always the transformation which behaves well, not taking image but inverse image. Okay, so that's why I mean we usually use inverse image. Image doesn't behave well. Yes.
Use open in y olmayacak mı? Whenever use open in y.
Evet, haklısın. So this should be y. Sağ ol. Okay. Okay, now a continuous bijection. Bijection means one-to-one and onto. A continuous bijection f from x tau x, y tau y, where since it is a bijection, there is all, of course, the inverse map going the other way from y to x is also continuous. Is called a homeomorphism. Okay. In this case, The topological spaces are called homeomorphic. This means what? This means the following. Actually, X and Y set-wise the same sets, right? There is a bijection. You just rename your set, I mean elements of your set, nothing different than that, right? They are equivalent sets. There is a bijection between them. And F and F inverse are both continuous, means image and pre-image of any open set is open. In other words, a set in X is open if and only if its image is open, and vice versa. So not only the sets are the same, but the topologies are, your open sets are also the same, okay? And in this case, we call them homeomorphic, and we will regard them as the same topological space. We will not distinguish them. In this case, so homeomorphic spaces will be regarded as equivalent or the same. Okay. Okay, now we will see a way of describing topologies. One way, of course, is to list or describe all the open sets, but usually it is not, I mean, convenient to list all the open sets because there are just too many. Instead, we describe a subset of the topology which generates all the open sets, but that subset is easy to describe, okay? And we will call it a basis for the topology. It's like, vector spaces. Instead of listing all the vectors, you just give a finite set of vectors, and then you say that every vector is just a linear combination of these. So it's something like this, okay? Basis and sub-basis. Let X tau be a topological space. A subcollection beta of open subsets of X tau is called a basis of the topology if the following is satisfied. For any u and x open and a point x in u, there is some b in this collection. So this is a sub collection of all open sets of the topology. So that x is in b and b is contained in u. Okay. If this is the case, then we say that B is a basis for a topology. I mean, for the topology tau. Okay. Tabii burada şunu da görüyoruz. Yani şey de var değil mi? Bu şunu gerektiriyor. Note that any open set u in x can be written as you see, for each point in u, you have some b containing that point, and this is of course an open set also, but that lies inside u. Therefore, I can write this as follows, this set, right? U, but each x here, let me just call this point, this open set bx, let's say. Okay, so for each x there is some bx, and then this can be written like this. But on the other hand, this bx already contained in u, therefore each bx is contained in u, therefore their union will be inside u. And this means what? I started with u, ended up with u, so this means u is just union of this bx's. In other words, every open set is a union of these basis elements. Okay. For example, in the standard topology in Rn, we may take those open sets, or sorry, basis elements as usual balls, right? Pardon, şunu silecektim. As an example, consider Rn with standard topology. As a basis, for example, we may take the following gadgets as a basis. One basis actually could be this, just balls with center X and radius R. X is in Rn and R is a positive real number. This is a basis, right? This is a basis. Another basis, instead of this balls, I may take boxes. So intervals like this, X, okay, A1, B1, AN, no, I'll have to take open intervals, of course, A1, B1, AN, BN. Okay, so here AI, BI, these are real numbers. So in this case, a basis element is something like this. In this case, a basis element is a box like this. Okay. Both of them describe the same topology. Why is that? Because you see, whenever you have an open set in Rn, okay, whenever you have an open set in Rn, every point has a neighborhood like this, sitting in that open set, and also has a neighborhood like this. Okay, so you may either use this basis as your basis of your topology, or you may use this one or any other thing. And actually in calculus, sometimes we use this gadget, sometimes we use this gadget, right? Depending on what you are going to do. Aranızda topoloji almış olanlar var mı? Vardır herhalde. Değil mi? Tamam. Sizin için birazcık şey oluyordur. Sıkıcı olabilir ama. Evet. Şey lafını etmiştik zaten değil mi? Stronger, finer. Yok onu söylemedim ama tam tanımlamadım. Let T1 and T2 be two topologies. On the same set X. We say that T1 is stronger or finer than T2 if T2 is a subset of T1. So the topology which has more open sets is called stronger, okay, or finer. And similarly, we say that in this case, Tau2 is weaker topology, okay? Okay. Now let me now describe how one can obtain new topologies from an given topology, new topologies from old ones. One of them is subspace topology. So what are we going to do? We will start with the topology, and using that topology, we will try to obtain new topologies. One of them is subspace topology. So let X tau be a topological space. Any subset. Şunu ışığını yakayım ya. Bu karanlık burası. Any subset A of X inherits a topology from X called tau A, described as follows. Yok, bunu zaten şey yapmıştık. Kalsın o. Şuraya. Tau A is the following topology. So I have to tell you what the open sets of this topology are. They are the followings. You just take intersection of A with all the open sets of your topology of on X, okay? You just intersect the open sets of the bigger space with your subspace, okay? With your subset. Of course, one has to show that this is a topology. So let me just leave it as an exercise. Show that this thing is a topology on A. Okay. Example. Zamanım var mı? Bitti mi yoksa? Evet, bitmiş. Let me give a break, and after the break I'll continue. Kaydı durdurayım. Tamam.